Advanced Higher Electromagnetism, Inductance. Inductors. An inductor is a component that has similar properties to a capacitor in that it can store energy and reacts to different frequencies in an AC circuit. An inductor is simply a coil of wire with very little resistance, that is negligible resistance, that uses the growth and decay of magnetic fields in its operation. We've already met this before in National 5 when we studied electromagnetism, and then in higher when we started looking at magnetic field generation. A magnetic field is generated when current goes through a current carrying wire. The symbol for an inductor is simply a line showing a coil with a wire above it. Self-inductance of a coil. We know that if we put current through a current carrying wire, a magnetic field is generated. But the opposite is also true. If a magnetic field or a magnet is moved in and out of a coil of wire, an alternating voltage is induced in the coil. Moving the magnet in one direction generates a voltage moving in that direction, and then in the other direction induces a voltage in the opposite direction. Therefore, we have alternating voltage. The size of the induced voltage depends on the size of the core, or the length of the coil, the strength of the magnet, or the magnetic field, and the rate of change of the motion of the magnet. That is, if we move the magnet backwards and forwards more quickly, we induce a higher voltage. If we increase the strength of the magnet, we induce a higher voltage. And if we increase the number of coils or the surface area of the wire, we increase the induced voltage. Now please note that the induced voltage does not require any external power supply and is therefore called self-inductance of the coil. Inductors in DC circuits. Here's a basic diagram of an inductor coil within a circuit where we have a power supply. In a DC circuit, when the circuit is switched on, there's a sudden change in current. We had no current, and then all of a sudden we have a current. Now this sudden change in current produces a changing magnetic field. That changing magnetic field generated around the coil will generate a self-induced EMF. This EMF across the coil acts in the opposite direction to the EMF supplying. So the EMF across the coil opposes the change in current that caused it. So let's revise that again. We turn on the circuit. There's a quick change in the current, which causes a changing magnetic field in the coil. The changing magnetic field in the coil induces a voltage. The induced voltage opposes the change in current that caused it, so it's acting in the opposite direction. Because the induced voltage always opposes the changes, we call it the back EMF. The induced EMF in a coil that opposes the change that caused it is part of what's known as Lenz's law, and it's a common topic in advanced higher projects. Back EMF and the rate of change of current. So here we have a graph showing how current varies with time in an inductor circuit. We can see that initially the current is going up at a very high rate. The rate of change of current is high. And that's because effectively the only thing that's limiting the current here is the resistance in the circuit. So we see at the beginning of the graph effectively a directly proportional relationship. However, when the circuit is initially switched on, we have that large rate of change of current, as we can see from the gradient. but that causes a large changing magnetic field around the inductor. That large changing magnetic field around the inductor, in turn, induces a large back EMF across the coil. Now, the back EMF always opposes the direction of the current that caused it. This means that that backwards EMF now slows down the rate of change of the current which caused the back EMF. And this causes then the back EMF to decrease. So the back EMF is caused by the rapid change in current. So a large rate of change of current causes a large backwards EMF. The backward EMF reduces the rate of change of current, and by doing so, reduces itself, until eventually the rate of change of current flattens out, there is no backwards EMF, and we end up with a constant current. We can determine the gradient of the graph by differentiation. The gradient di with respect to dt will decrease to zero as the back EMF decreases to zero as the current reaches its maximum value. When the current has reached its maximum value, there is no change to the rate of change of current, and therefore no magnetic field is being produced, no backwards EMF is being produced. Note that at the instant of switch on, the very, very instant switch on occurs, the backwards EMF is equal and opposite the supply voltage. Inductors and DC. The growth and then subsequent decay graphs of current in an inductor and a DC circuit are similar to what we see in the charge and discharge graphs of voltage for a capacitor. And you should remember the shape from higher physics. We can see that at switch on, we have a dramatic increase in current. That's a large rate of change of current. Eventually, this peaks, and then I end up with a constant current. When switched off, we have a dramatic decrease in current, but that rate of change of current eventually gets smaller and smaller until we have no change in the current and it becomes constant at a value 0. When switched on, it takes time for the current to reach its maximum value. Similarly, it also takes time for the current to fall to 0, just like we see in a capacitor. Inductance of an inductor, L. The inductance of an inductor is the ratio of the induced backwards EMF to the rate of change of current. That is how fast current is changing. The equation for this, as is on your relationship sheet, L is equal to negative EMF over di with respect to dt. The negative sign is because the EMF is the back EMF and opposes the direction of the current. It's going in the opposite direction. So epsilon here is the back EMF measured in volts. di with respect to dt is the rate of change of current, amperes per second. And L is inductance. Minus sign is because the back EMF is in the opposite direction to the forward current. We see this on the relationship sheet. Now the unit for inductance is the Henry, but if we consider the units for voltage and the rate of change of current, we could also say that 1 Henry is equivalent to 1 volt second per ampere. Because inductance opposes the flow of current, we could also consider it to have the units of ohms. The Henry unit is named after Joseph Henry, who is America's answer to Michael Faraday. Example. A 0.40 Henry inductor of negligible resistance is connected in a circuit as shown in figure 10. Switch S is initially open, then switch S is closed, you're asked to sketch a graph of current against time giving numerical values on the current axis, then fully explain the shape of the graph, and calculate the initial rate of change of current when switch S is closed. So here's our question. Let's look at each part. First of all, for part A, we need to sketch our graph. But before we sketch our graph, we need to determine the value of the current. Well, just like in a capacitor, the initial current, the charging current for a capacitor, is equal to the EMF divided by resistance. So I is equal to E over R, which is equal to 9 divided by 18, which is 0.5 amperes. We only need to consider the load resistance within a circuit because we've been told that the inductor coil has negligible resistance. 0.5 amperes. We have our graph for current and time as we saw previously. We need to explain the shape of the graph. The graph is just showing us that we have a large rate of change of current, which produces the back EMF and opposes the growth of the current further. So it's not enough for you to simply say that the rate of change of the current is decreasing. You need to explain why it's decreasing. And that's because the back EMF opposes the growth of the current. In part B, we're asked to calculate the initial rate of change of current when switch S is closed. Remember our equation. We rearrange this to find out the value of the backwards EMF. So backwards EMF is equal to negative the inductance multiplied by the rate of change of current. The rate of change of current is equal to the EMF divided by the inductance, giving us a value of 22.5 amperes per second. Energy stored in an inductor. Inductors can store energy in a magnetic field around them, which is different to the way that energy is stored within a capacitor. This energy is then released when the field collapses and the large EMF is produced. So we have energy stored within the magnetic field. That energy has come from the moving current going through it. However, that energy, when the magnetic field collapses, doesn't just disappear, it has to go somewhere, and it goes to produce a large EMF in the opposite direction. Remember, EMF, a potential, is giving work to charges. In this case, the work energy is given to the charges is in the opposite direction from where they came. So this is similar to a capacitor, and we have a similar equation for the energy. In a capacitor, E is equal to half CV squared is one of the equations we use for calculating the energy in a capacitor. The energy stored in an inductor is given by E is equal to 1/2 L multiplied by I squared. So you can see it's a similar relationship. The equation for the energy stored in an inductor is contained within the relationship sheet. Now this energy can be released really quickly when a large coil is switched off. So in a large coil, remember, if we want to increase the size of a magnetic field induced, we have a large coil. Now that quick release of energy can cause a large spark. That spark can damage equipment. Damaging equipment could potentially cause a loss of data or cause an electric shock. It's a surge. Now, similar to a capacitor, an inductor has a reactance. That is something like a resistance value which is dependent on the frequency of the source. A reactance is going to be very much like a resistance in that it will oppose the flow of charge. An inductor is another frequency-dependent component. When placed within an AC circuit, the inductor has an inductive reactance XL, which depends on the inductance of the inductor, the frequency of the AC supply. just like the capacitor reactance is dependent on the size of the capacitor and the frequency of the supply. However, the equation for inductive reactance is different. Inductive reactance XL is equal to 2 pi FL, not 1 over 2 pi F, which is what we see with a capacitor. So remember, reactance is similar to resistance in a DC circuit, but is entirely frequency dependent. Therefore, we can only have a reactance with an AC supply. Because it's similar to resistance in that it opposes the flow of charge, it has the units of ohms. And similar calculations we carried out as we saw with capacitive reactance, where XL, the inductive reactance, is equal to VRMS over IRMS. Example. Here we have an inductive circuit. We need to first of all calculate the inductive reactance of the inductor in this circuit, then calculate the effective current, the RMS current in the circuit when the supply voltage is 120 volts RMS and the frequency is 60 Hertz. And then the frequency of the supply is increased to 400 Hertz. State what happens to the reactance of the inductor and the current in the circuit. So you see this question is very similar to what we saw before in the capacitor video. However, we're using this so we can see the distinct differences between the frequency response for an inductor and the frequency response for a capacitor. So you can pause the video and have a shot yourself. Here are the answers. And on the next slide, we'll have a look at the solutions. So here's our circuit in the example. Calculate the inductive reactance of the inductor in the circuit. Well, inductive reactance, XL, is equal to 2 pi F multiplied by the inductance. So that's 2 times pi times 60 times 0.3 henries, which is equal to 113. And normally we would choose ohms as our unit. In part B, we need to calculate the effective current IRMS of the circuit when the supply voltage is 120 volts VRMS and the frequency is 60 Hertz. So we've already worked out our inductive reactance. We said that was equal to 113 ohms. Remember that that is also equal to VRMS over IRMS, which we can rearrange, and then just say that IRMS is equal to VRMS divided by XL. So that's 120 divided by 113, it's approximately 1.1 ampere. Next, we're asked to say what happens to the reactance of the inductor and the current in the circuit when the frequencies increase to 400 Hertz. Let's look at our equation. The inductor reactance is equal to 2 pi FL. What this means is that the reactance of the inductor is directly proportional to frequency and directly proportional to inductance. So if the frequency has increased to 400 Hertz, that means XL, reactance, has also increased. Remember, reactance is very similar to resistance, but for an AC circuit. So if the reactance is increased, that means the current has decreased. Because we can say that current is inversely proportional to reactance. So whereas for a capacitor circuit, we see that we have inverse proportional relationship with frequency and capacitive reactance, we have a directly proportional relationship for inductive reactance and frequency. In capacitance, we see that current is directly proportional to frequency. For inductance, current is inversely proportional to frequency. Similarly, is inversely proportional to inductance. Applications of capacitors and inductors. So capacitors and inductors are both reactive components. However, they react in opposite ways. For a capacitor, the capacitive reactance is going to increase as the frequency goes down. Whereas with the inductive reactance, that's going to increase as the frequency increases. So they're used in audio systems as filters. The filters will ensure that the correct audio frequencies are sent to the correct loudspeakers. We have different loudspeakers for different jobs. Capacitors have a low reactance at high frequencies, and inductors have a low reactance at low frequencies. A capacitor is used in series with the tweeter, which is the speaker which produces high frequency sounds, treble, like voice. An inductor is placed in series with the woofer that produces low bass sounds, for example, background atmospheric music. Another example is a defibrillator. The defibrillator, or AED, is used to restart the normal beating of a normal person's heart. It's a common misconception that defibrillators start a heart that has stopped. It's incorrect. What defibrillators do is they take a heart that's beating in an irregular rhythm or very, very fast and momentarily stops it, allowing the heart to then restart beating at a normal rate. So we see here in a circuit, we have a capacitor and inductor. Notice how the capacitor and the inductor are not placed in the same series connection as we would normally have for a capacitor circuit with a resistor. We have a DC supply. This charges the capacitor. When the switch is moved to position 2, the capacitor will then discharge. So the capacitor is charged up to a high voltage, switch is pressed, and the capacitor is discharged through the patient. Now the inductor is there to oppose the change of current. And this ensures that current is delivered to the patient at a high level for the required amount of time. An inductor is used instead of a resistor to ensure that all of the energy is passed to the patient and not wasted as heat in a resistor. Here's an example from the 2017 paper. A capacitor and inductor are used in hi-fi loudspeaker circuits. Explain why a capacitor is used in series with a tweeter. Explain why the inductor is used in series with the woofer. You're told when the frequency of the signal is 3.0 kilohertz, the capacitor and inductor both have a reactance of 8 ohms. And you're asked to find the capacitance of the capacitor and the inductance of the inductor. So this would be a good opportunity to pause the video and have a shot at this question yourself. Here are the answers, and then we're going to look at the solutions. So in the first part of the question, we're asked to explain why a capacitor is used in series with a tweeter. Now they're in series, so they're both going to get the same input signal. The capacitor is there to allow high frequency signals to pass, because remember, when we have a high frequency, we have a low capacitive reactance and therefore a high current. We could also say, as well as in allowing high frequencies, they block low frequencies. So allowing high frequency signals to pass, you'll find that if you have, say, for example, a surround sound system or a sound bar, it's the high frequency sounds which are coming from the sound bar, and then low frequency sounds coming from the tweeter, coming from the woofer. So what we want is we want the high frequency sounds to come through the speaker of the sound bar, and the low frequency sounds to go through the speaker that is the woofer, which is you have normally at the back of the room. In part B, we're asked to explain why the inductor is used in series with the woofer. Well, it's the opposite that we have for the capacitor. What the inductor does is it allows low frequency sounds or low frequency signals rather to pass, or we could say it blocks high frequency sounds. So in the last part of the question, we're told that when the frequency of the input signal is 3 kHz, the capacitor and the inductor both have a reactance of 8 ohms. And what we need to do is calculate the value of the capacitance of the capacitor and the inductance of the inductor. In order to do this, we simply need to use the appropriate reactance equations for each. So for the capacitor, capacitance reactance is equal to 1 over 2 pi fc. We substitute in the values. 8 is equal to 1 over 2 times pi times 3000, because it's kilohertz, multiplied by C. And when we rearrange and solve, we end up with a value of our capacitance to be 6.6 microfarads. Part 2, the reactance of an inductor, XL, is equal to 2 pi FL. 8 is equal to 2 times pi times 3000 times L. So L is going to be 8 over 2 times pi times 3000, which gives us a value of 424 microhenries, or 0.4 millihenries.